All right, guys, so now let's take a look at a problem like this. We've got 2 sine squared x plus 3 cosine x minus 3 equals 0. We're finding ourselves in a bit of an interesting position because our normal tactics up to this point aren't going to work on this. We can't isolate the trig functions as they stand. We can't really factor because we have 2 different trig functions. It would be like having an x and a y in the same problem. We can't factor that. We're a little bit stuck. So now we need to rely on what we've learned before and bring that back to the front of our mind. This problem, though, has a sine squared x in it. And that sine squared x is paired with a cosine x. Anytime you see a squared function paired with a different function in this type of problem, in these trig equation types of problems, think about your Pythagorean identities. Oftentimes, these are going to be what help you out. The Pythagorean identities, if you remember, are sine squared x plus cosine squared x equals 1. And then we've got 4 trig functions left. Put the 2 that don't have the c's in alphabetical order. We've got secant squared x minus tangent squared x equals 1. And then we just throw the cos in there. We have cosecant squared x minus cotangent squared x equals 1. Different teachers use different versions of the Pythagorean identities, but this is what I have come up with that helps me remember them the way they are. So I think of the first Pythagorean identity. I've got sine squared x plus cosine squared x equals 1. And it's going to be particularly helpful in this problem because our sine squared x, like I said before, is paired with a cosine x. So if we take our Pythagorean identity, sine squared x plus cosine squared x equals 1, and we solve for sine squared x, we get sine squared x equals 1 minus cosine squared x. We can then take this and plug it in for sine squared x. So what we have is 2 times 1 minus cosine squared x plus 3 cosine x minus 3 equals 0. And now with a little bit of simplification, we're into one of those factoring types of problems that we're able to solve. I'm going to go ahead and distribute my 2. I get 2 minus 2 cosine squared x plus 3 cosine x minus 3 equals 0. I'm going to combine my constant terms. So I have negative 2 cosine squared x plus 3 cosine x minus 1 equals 0. And me personally, I like to always have a positive lead coefficient. So I'm going to multiply the entire problem by a negative 1, and distributing that negative 1 through on the left side, I have a 2 cosine squared x minus 3 cosine x plus 1 equals 0. So now pause the video, take as long as you need, but see if you can figure out this problem from here, and then push play once you have it. All right, so from here I could use the quadratic formula, or I could just factor. I think factoring is pretty easy for this one, so that's the route that I'm going to choose to use. I get 2 cosine x minus 1 times cosine x minus 1 equals 0. I'm going to pause for just a second. I'm going to multiply back through and make sure I didn't make any mistakes in my factoring. If you make mistakes in your factoring, it can be really costly in the problem overall, so you've got to double check. Or at least it's a good idea to double check that you didn't do anything wrong. And factor however you factor, however it makes sense for your brain. From here, I'm good to go, so I'm going to go ahead and set this guy equal to 0, this guy equal to 0. I get 2 cosine x minus 1 equals 0. And I have cosine x minus 1 equals 0. Adding 1, dividing by 2, I get cosine x equals 1/2. And now I'm looking for an adjacent over a hypotenuse. So katoa, an adjacent of 1, a hypotenuse of 2. That happens, an adjacent of 1, hypotenuse of 2, with a 1, 2 square root of 3, and a 1, 2 negative square root of 3. That makes little 60-degree reference angles. And so I currently have 60 as an answer and 300 as an answer. Now jumping over to the other side, I have cosine x equals 1. Because it's 1, I'm going to switch to the quadrantal angles. I'm going to look at a curve. When does cosine x equal 1? That happens here and here. That happens at 0 and 2 pi. So if we looked at all of these answers on a single axis, we would have 0 and 2 pi. Then we would have 60, and we would have 300. So what I'm checking for there is any angles that might be going back to back so that we would make little half circles, or if all the angles together ended up making even intervals all the way around the axis. That didn't happen for this problem. And so for each of these angles, we're going to be spinning in full circles around that axis. So from here, I start with the smallest one. I get x equals 0. I'm going to spin in a full circle, 2 pi n. That I could simplify to just 0 plus 2 pi n is 2 pi n. My next angle is a 60, so that's going to be pi over 3. Spinning in a full circle, you have plus 2 pi n. And my next angle is 300. That's 5 times 60, so it's going to be 5 pi over 3's plus spin in a full circle, 2 pi n. I've got those three answers. If this problem had been set on an interval from the very beginning, for example, if this problem had said solve 2 sine squared x plus 3 cosine x minus 3 equals 0 on the interval 0 to 2 pi, we would have worked out everything the exact same, but at the end, we simply wouldn't have had the 2 pi n spinnies around the circle. At the end, if we were on the interval 0 to 2 pi, our answers would have just been 0, pi over 3, and 5 pi over 3. We just wouldn't spin forever and ever. Now, what would we have done if that problem didn't have the square in it? For example, what would we do for a problem like this? Cosine x plus 1 equals sine x. We have two different trig functions. We can't really isolate either one. I mean, we've got sine x isolated, but it's not separated from the other trig function. And we can't use Pythagorean identities because they are not squared. So if they're not squared, then let's just fix that problem. Let's square them. But be aware, this is the type of problem where students tend to make silly algebra 2 type of errors. For example, when they square, they don't actually FOIL. Or they'll do something kind of like this. Starting again with this problem, we've got cosine x plus 1 equals sine x. Students might be tempted to put both trig functions on the same side. So you'd have 1 equals sine x minus cosine x. Now, like we talked about a second ago, we're going to square this entire problem. And when you square sine x minus cosine x, it does not just become sine squared x minus cosine squared x. That's bad. That's wrong. Instead, you have to FOIL. You have sine x minus cosine x times sine x minus cosine x. And when you FOIL, when there's two trig functions on the same side, you get this little combo term in the middle. You would end up with sine squared x minus 2 sine x cosine x plus cosine squared x. And this combo term, depending on the problem, depending on the trig functions, can end up causing a lot of problems for you. Now, honestly, in this particular problem, it actually works out okay. But in general, there's no guarantee. And so you're going to want to keep your trig functions separate. So now circling back around, again, we've got the two different trig functions here. We can't completely isolate either one. They're not currently squared because they're not. And so to fix that problem, we're just going to square them. So we're going to square both sides. And so what we have is cosine x plus 1 squared equals sine squared x. Cosine x plus 1 squared, we're going to have to FOIL that. Always remember to FOIL. It is such a common mistake. Students don't FOIL properly and it blows up the problem. So we have cosine squared x plus 2 cosine x plus 1 equals sine squared x. We've squared the problem, and now we can use the Pythagorean identities to change sine squared x into cosine of some sort. Think of the Pythagorean identity that deals with sine and cosine. I know that sine squared x plus cosine squared x equals 1. So I can say sine squared x equals 1 minus cosine squared x, and I can substitute that in right here for sine squared x. I have cosine squared x plus 2 cosine x plus 1 equals 1 minus cosine squared x. So now I get everything on one side. I get 2 cosine squared x plus 2 cosine x equals 0. Pause the problem here and try to solve it the rest of the way. All right, so you're back. I factor out a 2 cosine x. I have 2 cosine x. That'll give me a cosine x plus 1 equals 0. This little guy equals 0. This little guy equals 0. 2 cosine x equals 0. Dividing by 2 gives me cosine x equals 0. On the other side, we have cosine x plus 1 equals 0. Subtracting 1 gives me cosine x equals negative 1. So now I look, and I have cosine x equals 0 at 90 and 270. Cosine x equals negative 1 at 180. And of course, we would convert to radians at the end. I'm hoping you got this far, but there's a little bit of a catch with our answers. Currently, like I said, we've got pi over 2, we've got pi, and we've got 3 pi over 2, or if you wanted to continue working in degrees, that would be okay. The problem is, at the very beginning, when we had cosine x plus 1 equals sine squared x, equals sine x, and we squared the whole problem, by squaring the entire problem, we created the possibility of extraneous solutions. Consider this, for example. If I said solve for the equation, solve for x equals 3. Super easy, I'm done, I solved it, x equals 3. But starting over, if I start again with the same equation, x equals 3, but I solve a squared version of it, I get x squared equals 9. That's going to give me x squared minus 9 equals 0. Factoring gives me x plus 3 times x minus 3 equals 0. We end up with negative 3 or positive 3. But clearly the negative 3 doesn't solve the original equation. Negative 3 does not work in the original non-squared version, which means negative 3 is an extraneous solution. Solving an equation by squaring the whole thing creates the possibility of answers that look like answers, but they're not really answers. So at this point, with our 90, 180, and our 270, we have to check our answers in the original equation. The original equation, remember, was cosine x plus 1 equals sine x. And we have to get rid of any answers that aren't actually answers. So I'm going to check pi over 2. Cosine of pi over 2 is 0, plus 1 gives me 1. Sine pi over 2 is 1. I end up with 1 equals 1. Pi over 2 works just fine. I'm going to try pi. I get cosine of pi plus 1 equals sine of pi. Cosine of pi is negative 1. Negative 1 plus 1 is 0. Sine of pi is 0. Therefore, 0 equals 0, and pi works also. So finally, I have to try 3 pi over 2. So I have cosine 3 pi over 2 plus 1 equals sine 3 pi over 2. Cosine of 3 pi over 2 is 0. 0 plus 1 is 1. Sine of 3 pi over 2 is negative 1. Negative 1 and 1 are not equal. Therefore, 3 pi over 2 does not work. 3 pi over 2 is an extraneous solution. So I have two answers, x equals pi over 2 and pi. I can now look at them on a graph and see if we have any back-to-back situations going on, or if we're dealing with full spins around the circle or some other interval. In this case, we're going to be dealing with full spins around the circle. I get x equals pi over 2 plus 2 pi n and pi plus 2 pi n. Always check for extraneous solutions before you finalize with the plus 2 pi n or the plus pi n or whatever interval you might be spinning with. All right, guys, I hope that makes sense. Talk to you later. Bye.